Hello, future engineers. Welcome to my YouTube channel. If you're still new to my channel and you like what I'm doing, please don't forget to share my videos to your friends and to your friends' friends. To your younger brothers and sisters who would want to take up engineering in the future, and to your relatives. That's one way you can keep me going, inspired, and refreshed. Now, if you find my videos interesting and important to your studies, also please don't forget to subscribe. So, hello students, subscribers, viewers, and future engineers. Here are another sample problem videos about problems on variation. So, though variation problems are easy to grasp and solve by constant practice, it will help you improve your thinking skills because as a starting point or starting problems to deal with in preparations to engineering life, you should have or you should start with light problems like this. The intensity, so problem 13, the intensity of light varies inversely as the square of the distance from the source. Compare the intensity on a screen that is 5 feet from a given source with that on a screen 7 feet from the source. So the solution is not animated so that I can present many problems, in this case about 6 problems for a short uh, file file size, for small size file size, so that it's easy for me to upload the video also. So for 13A, the intensity I varies inversely, so we have a constant of proportionality to the square of the distance to the source, or k over distance square. So I5 therefore is equal to k over, so we have here compare the intensity on a screen that is 5 feet from the given source with that on a screen 7 feet from the source. So when distance is 5 feet, so we have k over 25. That's the intensity of the light when the distance of that light is 5 feet from the screen. Then when the distance is 7 feet, k over 7 square is k over 49. Therefore, I5 over I sub 7 is k over 25 over k over 49. Cancel out k. So that's 49 over 25. So meaning the intensity of the light when its distance is 5 feet from the screen is equal to 49 over 25. 49 over 25 times that of the intensity when the light source is 7 feet from the screen. So that's the answer to the first. B. The amount of oil used by a ship traveling at a uniform speed varies jointly as the distance traveled and the square of the velocity. If a certain ship used 600 barrels of oil on a 300-mile trip at 20 knots, uh, I, this may be British barrels, but anyway, that's barrels. 20 knots, knot is nautical mile per hour, that's the original units. How much oil would it use on a trip of 100 miles at 10 knots? So let's set up the formula first. So the amount of oil, I'll call it A, amount is proportional to, so we have K, constant K, or varies jointly as the distance traveled and the square of the velocity. So this is the distance then square of velocity. So meaning if we solve for K, because K is not important here, it is A over dV squared. And we equate that to the initial condition A1 over D1 V1 squared. So the question is how much amount of oil would it use on a trip of 100 miles at 10 knots. So A, and we have distance 100 miles, then speed 10 knots, then quantity square equals, in the original or initial conditions, we have 600 barrels of oil, then distance 300 miles, speed 20 knots, so 20 square. Solving for A is 50 barrels. Then 13C, the wind force on a flat vertical surface varies jointly as the area of the surface and the square of the wind velocity. If the pressure on 1 foot square is 1 pound and the wind velocity is 15 miles per hour, find the force on an 8 by 10 feet 10-foot sign in a storm with a wind velocity of 60 miles per hour. So let's set up the formula first. Wind force on the flat surface varies jointly, so equals K as the area of the surface and the square of the wind velocity, so area velocity square. So therefore, if we solve for K, it is force over area V square. Then we equate it to the initial condition. We just put subscripts F1 over area 1 V1 square. So the question is the force on an 8 by 10 feet sign. So that means the area is 8 times 10, so 80. Then the wind velocity is 60 square in the final situation. Initial, we have a force of 1 pound on 1 foot square unit foot area. So 1 pound over 1 foot square. Then the wind speed 15 miles per hour, so 15 square. Solving for F is 80 times 60 square over 15 square, and that is 1,280 pounds. Problem 14, Part A, the strength of a rectangular beam that is supported at the ends varies jointly as the width W and the square of the depth D, and inversely as the length L. Compare the strengths of two beams if one of them is 20 feet long, 4 inches wide, and 6 inches deep, and the other is 10 feet long, 2 inches wide, and 4 inches deep. So formula for strength is equal to constant of proportionality. It is proportional, or it varies, strength varies jointly as the width W and the square of the depth, so D square, and inversely as the length L. So for the first beam, S sub 1, strength 1 is equal to constant of proportionality. It is 4 inches wide, so 4, then 6 inches deep, 6 square over 20. So take note that the numerator should be in inches, then the denominator is in feet. So there's no need to convert that as long as we consistently make the numerator dimensions in inches and the denominator in feet. So S1 is 36 over 5 of K. Then S sub 2 uh, equals K times the beam section is 2 inches wide, so 2 with depth is 4 inches, so 4 square divided by length 10 feet, so that is 16 over 5K. So getting the ratio S sub 1 over S sub 2 is 36 over 5K over 16 over 5K. We can cancel 5 and K. So 36 over 16, that's 9 over 4. So therefore, the strength of the first beam is equal to 9 over 4 times the strength of the second beam with these properties and dimensions. Then 14b, the horsepower required to propel a ship varies as the cube of its speed. Find the ratio of the power required at 40 knots to that required at 7 knots. So power is constant of proportionality, then cube of the speed. So power at 14 knots to power at 7 knots is K times 14 cube over K times 7 cube. We can cancel K, and that would be power at 40 knots. So the ratio of the power at 40 knots, horsepower required to propel a ship at 40 knots, so that for the power required to propel a ship at a speed of 7 knots is 8 as to 1. So you just call it 8 as to 1 because it is the ratio that is required there. And finally, 14C, the current I varies as the electromotive force E and inversely as the resistance R. In a system, a current of 20 amperes flows through a resistance of 20 ohms with an electromotive force of 100 volts. So find the current that 150 volts will send through the system. Because the system has constant resistance, it is 20 ohms. So it is still 20 ohms in the final situation. So I equals constant of proportionality. So times E, the electromotive force, and inversely as the resistance R. So therefore, if we solve for K, it is Ri over E equals R1 I1 over E1. So the question is, uh, if find the current that 150 volts will send through the system. So the resistance is still 20 ohms. Then this is the current in question divided by E, which is 150 volts. Then in the initial situation, we have 20 ohms as resistance. Then I is 20 amperes divided by 100 volts. Solving for I, it is 30 amperes. So that's it for this video.